Hello everyone! Today I will be solving problem 3.35 from Introduction to Electrodynamics by Griffiths. The problem states, a solid sphere radius r is centered at the origin. The northern hemisphere carries a uniform charge density ρ naught, and the southern hemisphere a uniform charge density negative ρ naught. Find the approximate field E of r and theta for points far from the sphere, where little r is bigger than big R. And we can start off by picturing what this sphere looks like. Okay, and we have the z direction over here and the y. And then just imagine x is over there. And we have a positive ρ naught on the northern hemisphere. And negative ρ naught on the southern one. Okay, and we know just from looking at this picture that for the E field, we can't have a monopole contribution because the total charge of this sphere is just equal to 0 due to the same but opposite values of the charge density. So what we want to focus on is the contribution from the dipole moment, and we have that that's equal to we need to find what this is. And so to use this equation, our dipole moment needs to be up in the z, needs to be facing the positive z hat direction and starting from the origin. So we have z over here. This is, we can just say a length z, but we have to go through the whole sphere, so there will be at some point an angle theta, and then it is going around the whole sphere, so phi goes from 0 to 2 pi. Oh yeah, and then let's remember this sphere has a radius of r. Alright, so to find what the dipole moment is, we know due to symmetry it will be on the z direction. So to find the dipole moment, we can just do the integral of z times the charge density, and it is a volume integral. So we're going to have two of these, one for the positive one, and then, two integrals. We're going to have one integral for the positive northern hemisphere and one for the negative southern hemisphere. And let's remember that d tau is just r squared sine theta d r d theta d phi. So when we take the integral of this, phi again goes from 0 to 2 pi. And then in this case, z is r cosine theta. Since this is our r, we have r cosine theta is equal to z. So if we keep writing our integral, we do the theta. So for the northern hemisphere, we're going from theta equals 0 to theta equals pi over 2. And then we have cosine theta, sine theta, d theta. And then we are going from r equals 0 to r equals big R. And then because we already have an r here, when multiplied by the d tau element, we have r cubed dr. And let's not forget that we also need to include the charge density. I'm going to write it at the beginning because it's a constant. So it's getting multiplied by this whole thing. So that's for the northern hemisphere. Now we want to add, I will also leave out the negative density here. We're going to do the southern hemisphere now. And this looks exactly the same, except one thing. And it's this integral. Now for the southern hemisphere, we go from theta equals pi over 2 to theta equals pi. All right, so the phi integrals basically come out to 2 pi. The integral of r cubed dr will just give us capital R to the 4th over 4. And again, that is the same for both. Now, for the integral, we can do u sub. So we can have u as sine of theta, and then the du would just be equal to cosine theta d theta. And for the positive hemisphere, the bounds go from, sine, and then sine of pi over 2 is just 1. So we would have 1. And then we have the negative from the negative charge density. So it's just minus, but now the bounds would be, we still have sine of pi over 2 is 1, but then sine of pi would just equal 0. So now we're going from 1 to 0, and it's u to u. And if we want to actually just switch the limits of integration, we just basically change the sign. And we end up with this. So we basically end up with a 2 when adding these two. So this becomes 4 pi rho naught r to the 4th over 4. And we end up with u squared over 2 from 0 to 1, which is just 1/2. So our total dipole moment, its magnitude is, this force cancel. So we end up with rho naught r to the 4th over 2. Oh, and I forgot the pi. Yeah, pi rho naught r to the 4th over 2. So if we plug back into our equation of the E field, we have pi rho naught r to the 4th over 2 over, when we go back, it's 4 pi epsilon naught r cubed. Okay, and by simplifying this expression, we get so we successfully found the dipole moment of this charged sphere, and we were able to find the electric field at points very far away from it as well. Thank you for watching.